A good operator with years of experience makes the job of normal boiler operation look easy. With a careful glance around the control room, this operator knows that the systems and equipment so important to the efficient production of steam are operating properly and according to plant procedures. In the event that a component malfunctions or something goes wrong, the operator sizes up the problem and quickly takes the appropriate steps to get the system back to normal. Making the operation of a boiler look easy, however, is not the key to being a good operator. The key is a thorough knowledge of the systems and components that make up the boiler, an understanding of how they operate, and the procedures for safe and efficient operation. In this program, we're going to look at the day-to-day, hour-to-hour routines that an operator follows during the normal operation of a boiler. Now, for our purposes, when I say normal operation, I'm referring to a condition where a boiler is operating continuously at or near design pressure and temperature. In other words, the boiler is working as it's designed to work, and steam is being produced hour after hour. Keep in mind that this is not the only way of defining normal operation. Depending on the way your plant is operated, your instructor may define normal operation differently. Now, the purpose of this program is to give you a basic overview of some of the typical duties that you'll be asked to perform when operating a boiler and some of the things you need to understand to generate steam efficiently. For the most part, the procedures for operating a drum-type boiler are similar to those followed when operating a once-through boiler. Throughout this program, we'll use a balanced draft, controlled circulation drum-type boiler as our primary example. However, when there's a significant difference between the procedures used for a drum-type boiler and those used on a once-through boiler, we'll stop and make those points clear. Now, as we progress through this program, we'll show you typical instrumentation that an operator monitors during boiler operation. We'll also indicate typical values for the unit we're using as an example. What you need to keep in mind is the fact that a given boiler is designed for a specific plant in a specific location. Consequently, designated values for your boilers will probably be different. Your instructor and your plant's procedures can help you adapt this information for your specific needs. You also need to understand that the procedures and operator checks that you'll see here are typically performed by more than one operator. No attempt is made to designate which procedures are performed by which operator for two reasons. First, operator responsibilities differ from plant to plant and unit to unit. Secondly, to ensure that normal operation takes place smoothly and efficiently, all persons operating a boiler need to be familiar with all of the procedures that apply to normal operation. Regardless of the procedures that a plant follows or the designated values necessary for normal operation, the reasons for having the procedures and maintaining the desired values remain the same. As in startup and shutdown, procedures indicate the proper method of operating all equipment so that the boiler is protected from damage and the people working in the plant are protected from injury. Another reason for procedures, which is especially important during normal operation, is efficiency. How efficiently your boiler operates is usually determined mathematically by comparing the amount of energy that goes into the boiler in the form of fuel to the amount of energy that leaves the boiler in the form of heat, which is contained in the steam. The formula for calculating efficiency is stated: percent efficiency is equal to the total energy out divided by the total energy in. When operated properly, a boiler is about 90% efficient. This means that of the total BTU content of the fuel going into the boiler, 90% of it leaves the boiler in the form of steam. However, regardless of how well the boiler is operated, energy losses occur. On the average, 10% of the total BTU content of the fuel is wasted. It's lost somewhere during the production of steam. A good operator wants to know where these losses occur and how to keep them at a minimum. By and large, the majority of the energy lost by a boiler occurs either up the stack or through the boiler casing. As this simplified diagram illustrates, most boiler casings are made of steel walls that are insulated from the boiler furnace by refractory and water wall tubes. Insulation keeps the majority of the heat produced by combustion inside the boiler furnace, where it can do work. However, you don't have to spend much time around a boiler to realize that it does give off heat. This heat is wasted energy. Fortunately, the heat escaping through the casing represents only a small percentage of the total heat produced by combustion. Well, there isn't much that an operator can do to control this kind of loss because it's a design factor. Cost studies and design factors have determined the amount of insulation necessary for efficient operation. What the operator can do is monitor the boiler to make sure that combustion is taking place properly and that losses do not increase. An operator will also check the position of the flame to make sure that it is not coming in direct contact with the water wall tubes, the casing, and other components. Direct contact can create hot spots on the boiler casing that allow more heat to escape. In terms of efficiency, an operator is most concerned with energy losses in the flue gas going up the stack. These are losses that an operator has greater control over. By now, you should know that boilers are designed to use the majority of heat present in the flue gas to produce steam. Now, this is accomplished by passing the gas over or through various components. These components include the superheaters, reheater, economizer, and air preheater. As this simplified diagram of a boiler tube illustrates, when the hot gas passes over the cooler tube, heat is transferred from the gas to the tube. The tube, in turn, transfers the heat to the water or steam carried inside. Anything that reduces the transfer of heat reduces efficiency and wastes energy. For example, ash, a non-combustible byproduct of combustion, tends to collect on tubes and other boiler components. When this happens, the ash insulates the tube or component from the heat of the flue gas. The result is that less heat is transferred from the flue gas to the water or steam inside the tube. And this means that more heat remains in the gas that is released up the stack, and therefore more heat is lost. We'll look at some of the methods for dealing with this problem later on in the program. In a little while, we'll begin looking at some of the basic procedures for safe and efficient boiler operation and some of the routine checks that an operator makes. For now, read over the material we've just covered in your text and answer the questions. If you have any questions or want additional information, ask your instructor to help you. Boilers have the capability of efficiently generating tremendous quantities of steam. One of the jobs of an operator is to monitor all of the systems on a boiler to make sure that the steam is being generated as efficiently as possible under the circumstances present at the time. Safe and reliable boiler operation depends on properly controlled combustion, maintaining proper flow rates on all systems, and utilizing the heat carried through the boiler by the flue gas. Unless these conditions are properly controlled, you aren't making efficient use of the energy supplied to a boiler. This in turn makes production of electricity more costly which hurts the economy of the plant and the community it serves. It can also harm the environment because it can waste natural resources and create pollutants. Efficient steam production is especially important to normal operation. Startups and shutdowns only make up a small portion of boiler operation. By and large, the boiler operates under normal conditions the majority of the time. Whether or not your boiler makes the most efficient use of the energy going into it depends to a great extent on how you operate it. The most efficient boiler operation is achieved under steady-state conditions. This means that the boiler is operating at a constant load and producing a designated steam output hour after hour with little or no fluctuation in the operating conditions. Steady-state conditions can be maintained at virtually any load. The output doesn't really matter. What's important is that a reliable supply of steam is being generated and that operating conditions of the boiler do not fluctuate radically. Achieving steady-state conditions involves a number of things. Chief among them are maintaining design steam pressure and temperature, maintaining proper combustion conditions, and maintaining design feed water flow, temperature, pressure, and level. On a drum-type boiler, steam temperature and pressure are the result of the firing rate and feed water flow into the boiler. During normal operation, a plant's operating procedures will indicate the appropriate firing rate for maintaining proper temperature and pressure. The operator must also carefully monitor the feed water flow to the boiler and make sure it's sufficient to maintain proper drum level. In this way, the operator can be sure that a reliable supply of steam is available for the production of electricity, while at the same time protecting the components in the steam water circuit from damage. This concern is slightly different on a once-through boiler. Steam temperature is the direct result of firing rate, while pressure is controlled by the output of the feed water pump. However, while the controls are different, the concern of the operator remains the same. That is, everything is operated according to procedure with little or no fluctuation. A second area of concern for achieving steady-state conditions is maintaining proper combustion conditions in the boiler furnace so that complete combustion takes place. By now, you should know that fuel, air, heat, and a chemical reaction are the four basic requirements for combustion. Complete combustion means that these requirements are combined in proper proportions so that everything in the fuel that is capable of burning does. All that is left over after combustion is complete is ash, carbon dioxide, water, and trace amounts of sulfur oxides and nitrogen oxide. From your knowledge of fuels and combustion, you should also know that complete combustion can occur in a number of ways. Stoichiometric combustion is one example. Stoichiometric combustion depends on every atom of fuel combining with a proportionate number of atoms of oxygen, allowing it to burn completely. Now, stoichiometric combustion is not possible in the boilers used in power plants. Therefore, boilers usually operate under off-stoichiometric conditions that are air-rich. That is, more air than is necessary for complete combustion is supplied to the boiler. This means that when a given quantity of fuel is burned completely, air is left over along with the ash, carbon dioxide, water, sulfur oxides, and nitrogen oxides. One of the ways that an operator has of knowing how well combustion is taking place is by monitoring excess oxygen in the flue gas. Excess oxygen, or O2, is an indication of how much additional air is being supplied to the boiler in order to maintain off-stoichiometric conditions. In this plant, efficient and complete combustion is achieved by maintaining excess O2 at slightly less than 4% of the flue gas. Some plants also have carbon dioxide, or CO2 indication, and carbon monoxide, CO indication in the control room. If complete combustion is taking place in the boiler furnace, carbon dioxide will be present in the flue gas. If you're getting an indication of carbon monoxide, then complete combustion is not taking place. When fuel is burned to CO rather than CO2, only about a third of the heating value is released from the fuel. This means energy is being wasted, and you need to take appropriate action to correct the problem. In addition to observing control room instrumentation, operators periodically make visual inspections of the boiler flame. Through experience and proper training, an operator can tell a great deal about combustion conditions by observing the flame in the boiler. The principal reason for a visual inspection is to verify that proper combustion is taking place. By observing the color, shape, and position of the boiler flame, an experienced operator can also tell how well fuel is burning, if airflow and fuel flow are properly matched, and how well fuel handling equipment is operating. The final aspect of steady state conditions that we'll cover is maintaining proper feed water flow, temperature, pressure, and level. In most plants, a boiler receives feed water from the condensate feed water system. The source of the feed water is condensate from the condenser. The condensate feed water system uses heaters to increase temperature and pumps to increase the pressure of the feed water being supplied to the boiler. By raising the temperature of the feed water prior to supplying it to the boiler, less heat has to be added to the water to produce steam. Heating also minimizes thermal stress on boiler components. Plant procedures will indicate the appropriate values for feed water flow, temperature, and pressure, and the way they are to be maintained in your plant. What's important for you to understand about steady state conditions is that all of the things that we've talked about must work in conjunction with one another. It won't do you any good to maintain proper combustion conditions, for example, unless you have an adequate supply of feed water for the production of steam. You should also understand that once these conditions are reached, they must be maintained with only minimal fluctuation if maximum efficiency is to be achieved. To aid the operator in this area, most boilers have automatic control systems that sense fluctuations and make appropriate adjustments immediately. These automatic systems are only as good as the operator monitoring them. An automatic system receives input signals from a variety of sources, processes the information, and responds much faster than any human could. However, automatic systems can't always see the big picture and may not always take the proper action. A good operator carefully watches his control room indications and double checks the automatic systems to make sure steady state conditions are maintained and that steam is being generated efficiently, safely, and reliably. In the next part of this program, we'll begin looking at some of the procedures for the normal operation of the steam water circuit. We'll also look at some of the basic checks that an operator makes during normal operation. For now, though, read over the section of your text that deals with the steady state conditions and answer the questions. If you have any questions about steady state conditions and how they relate to your plant, ask your instructor to help you. The operation of a boiler is a complex job that requires a great deal of training and experience to accomplish properly. To be a good operator, you have to have a complete understanding of all the systems and components necessary to operate your boiler. You need to know the desired values for such things as temperature, pressure, and flow for a number of operating conditions, how to achieve them, and how to maintain them to ensure steady state conditions. You must also know what effect changes in these values have on the production of steam and efficient boiler operation. Now, that's a lot to keep track of, and at first it's difficult to know just where to start. For the most part, all systems are monitored simultaneously. At any given moment, an operator may check airflow, drum level, fuel flow, and superheater temperature. And what the operator checks and why it's checked will depend on the situation at that time. In order to give you an overview of the basic responsibilities of an operator during normal operation, we've divided these duties into two parts. In this part of the program, we'll look at some of the operator responsibilities for monitoring the steam-water circuit. Later, we'll look at the operator's duties for monitoring combustion and the air-gas circuit. We've divided up the duties in this manner to make them easier to explain. As an operator, you'll be monitoring all systems simultaneously. You'll need to understand how these systems interact and what steps to take if something goes wrong. The components and systems that make up the steam-water circuit are chiefly monitored from the control room. Gauges, recorders, and other indicating instruments provide you with valuable information about how your boiler is operating. Periodically, an operator takes readings of these indicators to make sure that steady-state conditions are being maintained and to gather information that can be used to calculate boiler efficiency and plot power production and consumption trends. One of the readings that the operator is interested in is gross generation. This instrument indicates how many megawatts the unit is producing. Full load for this unit is 180 megawatts. When all systems are functioning properly and steady-state conditions are being maintained at full load, the indication will show a constant 180 megawatts. The temperature and pressure of the steam leaving the boiler is also a concern of the operator. Steam leaving the boiler must be hot enough and its pressure high enough to efficiently drive the turbine generator. This recorder indicates the main steam temperature leaving the boiler and flowing to the high-pressure section of the turbine. In this plant, under normal conditions, the main steam temperature should be 1,050 degrees Fahrenheit. This gauge indicates the main steam pressure. In this plant, a normal reading is 2,450 psi. A second recorder indicates the temperature of the reheat steam. That is, the steam leaving the reheater of the boiler and flowing to the intermediate pressure and low pressure turbine sections. Normal reheat steam temperature for this plant is 1,000 degrees Fahrenheit. Reheat pressure will vary depending on the load and operating conditions. The operator is concerned with gross generation and steam temperature and pressure because they are in part indications that the boiler is operating properly and that desired load is being maintained. To ensure that the boiler continues to operate properly and that a reliable supply of steam is available for the production of electricity, the operator must also monitor the water supplied to the boiler. On this drum-type boiler, drum level and condenser hot well level indication are important consideration for the reliable flow of energy through the boiler. Under normal operating conditions for this boiler, the steam drum is kept approximately 1/3 full of water at all times. This ensures that a sufficient supply of water is available for production of steam. If drum level is too high, then water may overflow into the superheaters and eventually get carried over into the turbine. If water level is too low, the water wall tubes and other components will overheat and possibly rupture. Careful monitoring of the drum level in the control room and periodic checks of the boiler drum keeps these problems from occurring. The boiler receives feed water at the economizer inlet from the condensate feed water system. The condensate feedwater system uses pumps and feedwater heaters to increase the pressure and temperature of the feedwater delivered to the suction of the boiler feedwater pump. By making sure that sufficient level is maintained in the drum and that the feedwater flow to the boiler is matched with steam flow out of the boiler, you're ensuring that a reliable supply of steam is available for the generation of electricity. You're also making sure that the components in the boiler are protected from overheating and damage. In addition to these responsibilities, an alert operator will also anticipate problems with the system and be ready to take appropriate action if a problem occurs. One such problem could be the loss or reduction of circulation in the boiler. This is a controlled circulation boiler that uses 2 boiler water circulating pumps. With both pumps operating, the unit has the ability to circulate enough water to produce 1,300,000 pounds of steam every hour. For this unit, that's sufficient to produce 180 megawatts. Circulation is monitored on this gauge in the control room. The gauge receives pressure indications from the inlet header and outlet header of the boiler water circulating pumps and indicates circulation by measuring differential pressure. If something goes wrong with one of the boiler water circulating pumps, the operator must adjust load accordingly. In this plant, one pump can circulate sufficient water to produce 860,000 pounds of steam per hour. That will allow the operator to maintain a load of 125 megawatts. Understanding the capacity of your unit when everything is operating properly and its capacity when things go wrong allows you to make instant decisions and take proper action so that steam production and electrical production are not interrupted. Now, most of the systems in the plant have automatic control devices that respond to changes in load and variances in conditions to keep things running smoothly. These automatic systems operate by maintaining certain control points. One example of this type of control is the rate at which combustion takes place in the boiler. If the rate is increased or decreased, the automatic control system immediately adjusts various flows to coincide with the change in these control points. A good operator monitors these flows to make certain that the automatic systems are operating properly. The operator may also make fine adjustments to systems manually because experience or plant procedures tell them that the unit will operate more efficiently and reliably when these adjustments are made. There are some systems, however, that can't be directly controlled by automatic systems. Control of these systems is limited by design factors and changes in prevailing conditions. Feedwater temperature at the economizer inlet is one example. The temperature of feedwater being supplied to the boiler is in part a result of load and partly a result of the design of the plant. Condensate feedwater systems that have a large number of feedwater heaters may supply feedwater at a higher temperature, while systems with fewer heaters may supply feedwater at lower temperatures. The economizer inlet temperature is also affected by how well the feedwater heaters are operating. An operator must be aware of systems where direct control is not possible and know how to correct any problems that may occur. As we said earlier, an operator must be able to monitor all of the systems on a unit simultaneously. What we've seen here are some of the instrumentation that let the operator monitor a unit and some of the concerns of an operator in regard to the steam-water circuit. In a little while, we'll continue looking at other responsibilities of an operator during normal operation. But for now, read over the material we've just covered in your text and answer the questions. Your instructor can help you apply that information to your plant's normal operating procedures. In this part of the program, we're going to cover some operator responsibilities concerning combustion and the air and gas circuit. We'll also look at some of the basic checks that an operator makes during normal operation. Now keep in mind that under normal circumstances, an operator does not monitor a boiler system by system. The operator monitors all systems at once and will concentrate on one system or part of a system depending on prevailing conditions. A typical operator controls a great deal of energy. He controls the energy going into the boiler by regulating fuel flow. Energy released in the boiler is controlled by firing rate. Energy leaving the boiler is regulated by control valves which control the flow of steam. To maintain steady state conditions and to generate electricity in the most efficient manner possible, an operator must be able to monitor the combustion conditions as they affect steam flow. A steam flow airflow recorder is one means of monitoring combustion conditions. This recorder receives separate input signals on the flow of steam leaving the boiler and the flow of air that's used for combustion. The steam flow airflow recorder is calibrated to indicate firing rate by measuring the air used for combustion and comparing it to steam flow, which results from the firing rate. When the steam flow and the airflow are matched, the operator knows that complete combustion is taking place and that steam is being produced efficiently. Now, this is only one of several indications of efficient operation. An operator is also concerned with the temperature of the fuel entering the boiler. This coal air temperature recorder indicates the temperature of the air and coal leaving the pulverizer and entering the boiler on this coal-fired unit. As you'll recall from earlier training, heated primary air is used to dry coal so that it can be pulverized and to transport the coal-air mixture to the burners. The coal-air temperature in the pulverizer must be watched to make sure that it's hot enough to dry the coal, but not so hot that it causes combustion inside the pulverizer. In this plant, coal air temperature is typically around 160 degrees Fahrenheit. However, it changes depending on the coal being burned. In conjunction with monitoring the coal air recorder, the operator must also monitor the temperature of flue gas leaving the boiler. Flue gas temperature must be carefully monitored to prevent energy from being wasted. If flue gas temperature is too high, then efficient transfer of heat is not taking place inside the boiler. This means that heat is wasted up the stack. By contrast, if the flue gas temperature is too low, condensation may form. When condensation forms in the presence of sulfur-laden flue gas, sulfuric acid is produced. Sulfuric acid can damage the stack and the ductwork that the flue gas passes through. In this plant, the operator tries to keep the flue gas temperature between 320 and 360 degrees Fahrenheit. The actual value changes because of the dew point. Dew point is the temperature and pressure at which condensation occurs. Many things go into figuring dew point, and most procedures will indicate how dew point is calculated and the proper flue gas temperature to prevent condensation. Ideally, that temperature will be close to, but not at, dew point. Flue gas results from the combustion process. The operator wants to make certain that combustion is taking place properly and that all of the energy present in the fuel is being released by combustion. As we've indicated earlier, most boilers operate under off-stoichiometric conditions that are air-rich. The excess oxygen recorder in the control room allows the operator to tell how much oxygen is left in the flue gas when combustion is complete. In this plant, efficient operation is maintained with slightly less than 4% excess oxygen in the flue gas. Each pen on this recorder is receiving information from different stacks. When complete combustion occurs, carbon dioxide is one of the byproducts of combustion. If incomplete combustion occurs, carbon monoxide will also be present. Some plants monitor the presence of carbon dioxide and carbon monoxide in the flue gas as a means of verifying that complete combustion is taking place. This recorder serves this purpose. The blue pen on the recorder indicates the percentage of carbon dioxide in the flue gas. Currently, it's a little more than 13%. The red pen indicates the presence of carbon monoxide. If the boiler is operating properly, no carbon monoxide should be present in the flue gas. As you see here, the indicator is 0. Carbon monoxide is an indication of incomplete combustion. Burning fuel to carbon monoxide rather than carbon dioxide only releases about 1/3 of the total heating value of the fuel. If your plant has a recorder like this, and you find that carbon monoxide is present in the flue gas, you should immediately take steps to eliminate it. In most cases, this will require adjusting either fuel flow or airflow. As you know, air and gas flow is necessary for efficient combustion. Gauges such as these are used to monitor the flow of air into the boiler and the flow of flue gas over the heating surfaces of the superheater, reheater, economizer tubes, and air preheater. This gauge monitors furnace pressure. These gauges show secondary airflow in the wind box. Now, monitoring control room instrumentation is a large part of the operator's job. In most cases, automatic systems help keep things running smoothly by responding to changes in conditions and automatically adjusting values accordingly. However, another part of the operator's job is to make sure that things continue to run smoothly and that situations don't occur that will affect the efficient production of steam. Part of the operator's normal routine is to periodically walk the system to make sure that everything is functioning normally. One thing he checks for are proper lubricant levels in all equipment and that bearings are not getting too hot. Here, an operator is checking the lubricant level on an air preheater. During the walkthrough, the operator also looks and listens for air, water, and steam leaks in or around boiler components. An air leak, for example, could affect the temperature of the boiler flame. Air leaks are usually indicated by a high-pitched whistle coming from the leaking component. The operator must also check the boiler casing for signs of overheating, buckling, and hot spots. Hot spots allow more heat to escape through the casing, which reduces boiler efficiency. Under extreme conditions, overheating and hot spots could cause the boiler casing to rupture. Usually, the operator finds hot spots by looking for blistering paint on the boiler casing or being aware of a burning smell near the overheating section of boiler. No walkthrough of a boiler is complete without making a flame observation. As we indicated earlier, an experienced operator can tell a great deal about the conditions of combustion and the production of steam by opening observation doors and looking inside. The location of hot spots, excessive slagging of components, and proper air and fuel flow can usually be checked by visually inspecting the boiler. No matter how carefully a boiler is maintained or how well an operator does his job, the facts of life are things do go wrong during normal operation. Annunciator alarms in the control room provide audio and visual indication when a problem occurs. Part of an operator's job is to respond to annunciator alarms and determine the cause and solution to the problem. In some cases, the solution may require nothing more than adjusting the flow rate of a feeder or the positioning of air dampers on a fan. In other cases, a piece of equipment may fail and maintenance is required. To correct the problem, in these cases, the operator is charged with the responsibility of tagging out the system or component and making sure that it is isolated and safe for maintenance crews to perform the necessary repairs. A basic rule of thumb for normal operation is to follow your plant's procedures and trust your automatic systems. If everything is functioning properly, leave it alone and monitor what's going on. If something goes wrong, determine the cause of the problem and take the appropriate action according to the procedures to correct the problem. Take some time now to read over the material we've just covered in your text and answer the questions. When we come back, we'll look at how an operator controls steam temperature in a boiler. By now, you should realize that boiler steam temperature is of great concern to the operator. The control of steam temperature is necessary for efficient and safe boiler operation. If steam temperature is allowed to get too high, components can overheat and melt. By contrast, steam temperature being too low wastes energy, reduces efficiency, and can even cause water droplets to carry over into the turbine. Maintaining proper steam temperature is the operator's responsibility. Earlier you saw some of the control room instrumentation that is used to monitor the temperature of the steam. In this part of the program, we'll look at a number of methods used to control steam temperature. The methods we'll cover include the use of desuperheaters, sometimes called spray attemperators, burner tilting, gas bypass, and gas recirculation systems, and soot blowing. An individual boiler doesn't usually have all of these methods of steam temperature control. In general, your boiler will have soot blowing capabilities and at least one or more of the other methods we mentioned for controlling steam temperature. We'll look at each of these methods, beginning with desuperheaters. In your earlier training, you learned that a desuperheater, or spray attemperator, as it's sometimes called, sprays a fine mist of water into the flow path of the superheated steam. As the water evaporates, it removes heat from the superheated steam, lowering its temperature. We'll use this simplified diagram to review how a desuperheater works. Superheated steam is flowing through this pipe. Here is the desuperheater. When in operation, the desuperheater sprays a fine mist of water into the superheated steam flow path. The superheated steam gives up some of its heat to the water. Since the superheated steam is hotter than the water used by the desuperheater, it causes the water to flash to steam. The result is the superheated steam temperature is reduced. Desuperheaters are generally located between the primary and secondary superheaters and in the inlet line of the boiler reheater. The typical procedure in most plants is to control the outlet temperature by desuperheating at the inlet. Now, whether or not your boilers use desuperheaters will depend upon their design. Ask your instructor if you're not sure. Another method of controlling steam temperature that is found on a number of boilers is tilting burners. As you learned earlier, burners can be designed to place a flame on, above, or below the horizontal plane. Changing the position of the boiler flame, you can directly affect how much heat is transferred to the boiler tubes. For example, with the burners positioned on a horizontal plane, the steam temperature recorder in this plant is indicating that the superheater outlet temperature is high. The operator decides to tilt the burners below the horizontal plane to reduce the amount of heat being transferred to the superheater tubes. We'll use this diagram of a typical burner to see what happens. When the burners are tilted down, more heat is directed to the water wall tubes. This means that the water walls will absorb more of the heat, leaving less available for superheating. In this case, the operator chose the proper action to return the superheater outlet temperature to normal. By the same token, if the superheater outlet temperature is low, by tilting the burners up above the horizontal plane, the superheater is exposed to more heat while less heat is transferred to the water wall tubes. The result would be an increase in superheater outlet temperature. Two other methods of steam temperature control are gas bypass and gas recirculation. Both methods depend on redirecting flue gas flow to increase or decrease heat transfer to various boiler components. We'll use this simplified diagram to explain the gas bypass method of steam temperature control. With this system, a portion of the flue gas is drawn out of the furnace area just before reaching the superheaters. The gas is directed through ductwork to a point just ahead of the economizer. A damper in the ductwork is used to regulate flow. By causing gas to bypass the superheaters, less heat reaches the superheater tubes and the steam temperature is reduced. Now, this heat is not wasted, however, because the hot flue gas passes over the economizer, which raises the temperature of the feed water entering the boiler. Gas recirculation works differently. As this simplified drawing illustrates, a fan draws a portion of the flue gas out of the gas flow path downstream of the air preheater. Now, this gas is recirculated to either the wind box or a point just above or below the burners in the furnace area. Gas recirculation accomplishes two things. First, it lowers the overall temperature of the flue gas, which in turn decreases the superheated steam temperature. Second, it reduces the formation of nitrogen oxides. Nitrogen oxides are pollutants and in most areas are regulated by law. Nitrogen oxides tend to form at high temperatures. By lowering the flue gas temperature, the formation of nitrogen oxides is reduced. The final method of controlling steam temperature that we discuss is soot blowing. Every boiler that you'll be operating will have soot blowing capabilities. How often they are used and the manner in which they operate may vary. Soot blowers are used to clean ash and slag deposits from boiler tube surfaces. Essentially, a soot blower is nothing more than a rotating pipe with holes drilled in it that sprays compressed air or steam near boiler tubes and other components in the flue gas path. Most boilers have a number of soot blowers located in various areas of the boiler. The size of the soot blower depends on the area of the boiler where it's used. Here, for example, is a long retractable soot blower used to clean superheater and reheater tubes. In general, the length of these soot blowers is roughly half the width of the boiler. By contrast, this is a wall blower. Wall blowers are shorter and generally located around the furnace area of a boiler. Like the long retractable soot blowers, wall blowers may also be retractable but only need to extend a few inches inside the furnace area. Regardless of the type or function of the soot blower, all soot blowers perform essentially the same job, that is, cleaning slag and ash off boiler tubes. Soot blowers are usually operated from a panel in the control room. Each soot blower is identified by a code number, which indicates its type and position in the boiler. Each blower can be activated individually or as part of a programmed cycle. To initiate soot blowing, an operator throws a switch on the panel that corresponds to the blower he wishes to operate. The operator then pushes the manual start button. On this panel, a green light comes on when soot blowing has started. When soot blowing is initiated, a drive motor begins inserting the soot blower into the boiler. This example is a wall blower. The soot blower rotates constantly, blowing steam or compressed air in a circular pattern near the water wall tubes. The spray dislodges ash and slag, which is built up on the tube surfaces. The constant rotation of the soot blower and the constant flow of steam or compressed air through the blower are important for two reasons. First, the rotating pattern ensures wide coverage of the cleaning medium. Second, rotation and constant flow through the soot blower prevent it from overheating. Plant procedures will indicate how often and in what sequence soot blowers are used. Soot blowing is the most common and most effective method used for controlling steam temperature. Ash and slag deposits on boiler tubes insulate the tubes and interfere with efficient heat transfer. By cleaning away the ash, heat transfer is increased. As I said earlier, your boilers will have soot-blowing capabilities and at least one other method of steam temperature control. Whether that method is de-superheaters, burner tilts, gas bypass, gas recirculation, or a combination of any of these will depend on the design of the boiler. Your instructor can give you specific information on the steam temperature controls in your plant. Now, take some time now to read over this material in your text and answer the questions. Ask your instructor to help you if you have any questions on steam temperature control. The final aspect of normal operation that we're going to cover is the operator's responsibility for removing the waste products of combustion. You just learned that boilers use soot blowers to remove ash and slag deposits from the boiler tubes. However, most of the ash and slag still remains inside the boiler. Ash handling is a normal part of the operator's daily routine. Ash is the non-combustible material that is present in all fuels. When complete combustion occurs, ash is the only solid material that is left over. Generally, ash is removed from the boiler on a regular basis and buried in large landfills. Your plant's operating procedures will indicate how often ash must be removed from a boiler and the method of removal and disposal. This plant uses two ash handling systems. A bottom ash system removes large chunks of ash that fall to the bottom of the boiler during combustion and soot blowing. The fly ash system removes fine particles of ash that are carried through the air gas circuit by flue gas. Let's look at the bottom ash handling system first. The bottom of this boiler forms steep-sided bins called ash hoppers. The ash hoppers are partially filled with water. The water serves two important functions. First, it quenches the hot pieces of ash that fall into the hopper. And second, the water serves as a conveying medium when the ash is removed. A gate located here separates the bottom of the boiler, where the ash is collected, from the rest of the ash handling system. Ash pulling is the name given to the process of removing ash from the boiler. Ash pulling is initiated by an operator who first starts a pump. This pump forces the ash-water mixture out of the hopper and through piping to a collection area. With the pump running, the operator next starts up the clinker grinder that is located beneath the gate on this hopper. Now, this is what the inside of the clinker grinder looks like. When the gate is opened, ash flows between these two rotating rollers. The rollers crush chunks of ash into a fine consistency that will stay suspended in the water. The operator next opens the ash gate. This allows the water and ash mixture to flow from the ash hopper through the clinker grinder and into piping, which directs it to a collection and disposal area. The operator opens flush valves to rinse away any deposits that may cling to the sides of the hopper. He then makes a visual inspection of the inside of the hopper by looking through an inspection window. When the operator is satisfied that the sides of the hopper are free of ash, he then closes the ash gate and fills the ash hopper to the appropriate water level. Bottom ash handling equipment removes the largest percentage of the ash produced by combustion. However, a separate system is required to handle fly ash. Fly ash consists of fine particles of non-combustible material that leave the boiler along with the flue gas. Fly ash is primarily a nuisance to a plant because it will stick to virtually anything. Various methods and means are used to remove fly ash from the flue gas. The majority of the fly ash is collected in large fly ash hoppers like these. Periodically, ash collected in the hoppers must be removed. Removal is initiated in the control room by starting up the fly ash system. A system control panel can take on a number of different configurations. This system uses a series of lighted panels to indicate what components are operating. Essentially, fly ash systems all work the same way. That is, when the operator starts the system, either a positive or negative pressure is exerted on the conveying piping connecting all of the components in the system together. Valves in the bottom of each hopper isolate the hopper from the conveying piping. In a predetermined sequence, the valve on a hopper is opened and the ash collected by the hopper is forced into the conveying piping. This indicator in the control room receives input signals that tell the system when a hopper is empty. The system then automatically closes the valve in the empty hopper and opens a similar valve in the next hopper in the sequence. For the most part, a fly ash system operates automatically once the operator turns it on. The operator must monitor the operation to make certain that everything is functioning properly and according to procedures. When the sequence is complete and all of the hoppers have been emptied, the system shuts off automatically. Both fly ash and bottom ash pulling are performed periodically during normal operation. How often ash pulling takes place is determined by plant procedures and the type of fuel being burned. Your instructor can give you specific information about ash pulling procedures in your plant. Normal boiler operation is a demanding job. In this program, we've looked at how an operator monitors the various systems and components that make up a boiler, routine checks that keep the boiler operating properly, and a number of methods which can be used to control the temperature of steam leaving the boiler. You've also seen how ash handling is accomplished to remove the solid byproducts of combustion from the boiler. Finally, throughout this program, we've stressed the importance of following your plant's operating procedures so that all systems are operated as efficiently as possible. Efficient operation is the key to becoming a good operator. Efficiency affects the cost of producing and supplying electricity, the cost of operating your plant, the conservation of natural resources, and most importantly, the health and safety of the people working in the plant. Take some time now to finish reading this portion of your textbook and answer the final set of questions. Remember, if there's anything that you want more information about, ask your instructor to help you.